Okay, so what today we are looking into is confirming correctness of an algorithm, right? So now why we say that we need to confirm the correctness of algorithm. See, I have designed an algorithm, correct? But how do I know whether that algorithm is working correctly for my given application or given solution? Correct, because there is some problem. For that particular problem we always try to find out the solution through algorithm. Now how do I confirm whether my solution is correct or whether my solution is incorrect? So for that purpose, what we need is we need to confirm this solution, confirm this solution of algorithm, right? So now for confirming the algorithmic solution, what we have is we have a well defined computational problem, correct? Now I will write it down. So what we have a well defined computational problem. Now this problem is consist of a triplet. What is that triplet? P of I comma O comma R. Correct. This problem is a triplet. It is represented. This computational problem is represented via triplets. This triplet is P of I comma O comma R. Now what is this I? I is a valid input, right? What is the O? O is a expected output, correct? And what is R? R is a defined relationship between I and O, correct? So here what we are doing is we are writing our given problem statement in a computational form, so which is called as a computational problem, which is given in a triplet format. Triplet format is P of I comma O comma R. So I is a valid input set, O is the accepted output set, and R is the defines the relationship between I and O. Correct. This R can be considered as a mapping function also. Right. What is this mapping function does? This mapping function translates our I to output O, correct, through that particular mapping function, which is R. Right. So the algorithm is solved is to solve a problem P if correct. Like the algorithm which we propose to solve a problem P is correct if and only if for all problem instances, I, right? For all problem instances, what are these problem instances? These are I, correct? So I will write it down. Problem instance is I, correct? This I belongs to capital I. That is a complete set, and it terminates and produces the output O. Correct. So how do I say that algorithm is correct? So when for my all input instance, correct, or all the problem instances, right, I get a output, a expected or the accepted output through a function R, then only I will say that my algorithm is correct. Correct. So it is very much necessary to prove the correctness of an algorithm. The simplest way to do this is to test the algorithm for a different input combinations, right, and compare the results manually computed or already available with the ground truth, right? So what we do in this case, the very simple way is we will have the dry run on every input case, all the corner cases of input, and then we will compare the output with computationally calculated output, right, or whatever is the ground truth with us, right? So this is actually you can say a very old way of checking the correctness of algorithm, because it is very time consuming, right? So what we have to do, we need to provide some way, correct, to prove the correctness of an algorithm, right? So for this case, we can do what we can do to prove the correctness of algorithm. We can check the before conditions, right? Those are preconditions, and after conditions, that is a post condition of the execution of each steps, right? So what we have to do to prove the correctness of algorithm is to check the condition before and after the execution of each steps. That is a very simple way, correct? So the algorithm is correct only if precondition is true, then post condition must also be true. This is the rule, correct? The algorithm is correct only if precondition is true, then post condition must be true. Fine. Now take an example of a problem of finding a factorial of a number. Correct. So this particular finding the factorial of a number, this algorithm definitely halts. We all know that this algorithm definitely halts after doing n minus 1 multiplications, right? How do we find the factorial of a number? Suppose I want to find out the factorial of 5, then I will do 5 into 4 into 3 into 2. Correct. So n minus 1 multiplication. So proving the correctness of this particular problem informally is very simple. Correct. When I have the input of say 4 or 5, it is very simple to prove this correctness. But suppose there is a large number of inputs. Say my number is 1, 2, 5, 6, 9, 8, 4, 5, 6 like this. Then can we check the manually the correctness of the proposed algorithm for a given problem? Right, it is very difficult when my input size is very huge. When my input size is very huge, it is very difficult to prove the correctness of an algorithm manually. Right, when an input size is very small, it is very easy to check the correctness manually. So for such cases, right, when there is an input size huge and then it is tedious to calculate manually or it is very time consuming, we need some method to prove the correctness of an algorithm, right? So what we can say that the algorithm for a real life problem often involves a loop. Correct, you must have solved many algorithms and they are having the loops. So correctness of such algorithm is proved through loop invariant property. Please remember how to prove the correctness of an algorithm. To prove the correctness algorithm having loops, we use loop invariant property. Understood all of you what I try to say? See, there is one property which is called as a loop invariant property. So to prove the correctness of algorithms which are having loops, we use this particular property, right? Now what does this property consist of? This loop invariant property, this particular loop invariant property consists of three steps. What are these three steps? Of the first is initialization, then we have maintenance, and the third one is a termination. So these are the three steps to check the correctness of an algorithm. Which algorithms which are having the loop? So this particular property is called as a loop invariant property. You can write it down here also, loop invariant property. What is this initialization? It is a condition, right? A conditions true prior the first iteration of the loop. Correct? In the initialization case, this condition must be true prior to the first iteration of the loop. What do we do in a maintenance? If the condition is true before the loop, it must be true in the next iteration also, or it must be true before the next iteration also. So this is your maintenance phase, right? So your property must be true throughout the loop iterations. That is your maintenance step. Okay. And then the last one is a termination steps. Now what do we have in a termination steps? Is on the termination of a loop, invariant gives us the useful property that helps us to prove the correctness of algorithm. What does it mean? During the termination also your invariant must be true. Correct. So we will see a very simple example to prove this correctness of an algorithm. Okay, is this okay with all of you? I hope you have understood this invariant property, and invariant property is okay with all of you. Correct. So a simple example, now we'll see a sample example. Okay. Now what we have in this sample example, a very simple example, find the maximum from the array of 10 variables. This is a problem statement in my hand. Correct. Now, what is the solution for this? See, I will have a solution. Solution is say a precondition. Precondition is max is equal to 0. Currently, initially, I do not have a max, so I will say a of I and I is equal to 0. This is my precondition. Correct. And now my algorithm starts. See, for I is equal to 0, I is less than n, I plus plus. What should I write after this? How do I find the max? Can anybody tell me? How do I find the max? If a of I is greater than max, correct? Max is equal to a of I. Am I right over here? I hope this step is clear with everyone. Correct. And now I will write a post condition as a variable max contains largest integer in A. Correct. And my I is equal to 10. Correct. Initially my I was 0. Say I have 10. I said I have, see this. I said I have, what I said, I have 10 elements. So my I is equal to 10. Correct. Now, how do I prove the correctness of this? Correct. How do I prove the correctness of this? What I have to say while proving the correctness is I need to go with this three steps. Correct. Initialization, maintenance, and a termination step. Okay. Now, what do I say for the initialization step? How do I say that for the initialization step? See, first is my initialization step. सो इन इनिशियलाइजेशन ठीक है अब क्या है इसमें लूप एन इनवेरिएंट प्रॉपर्टी आई विल से दैट लूप एन इनवेरिएंट होल्ड्स बिफोर द इनिशियलाइजेशन correct so what does it mean loop where invariant holds before the initialization say these are my loop invariants right so before the condition my max is a of 0 and I is equal to 0 correct so this is a trivial case correct and it proves that the loop invariant is true before the iteration because I have given the precondition over here and I say that my loop is true before the first iteration correct and then I have the maintenance steps. What will I do in maintenance steps? See, for the each iteration, right? There are iterations. See, these are called as iterations. I hope you all are there with me. These are called as iterations. So for each iteration, the algorithm finds the correct position of a max or the correct position of a maximum element. Correct? For each iteration, am I right? Because initially I say my a of I is my a of 0 is max. Correct. But suppose a of I is greater than suppose a of I is greater than max, then I do a swapping. Correct. So what I say at each iteration, I find the correctness of a max. Right. Or each iteration I find the corrected max correct then after the loop at the end of a loop what does happen what will happen at the end of a loop this max will have the maximum of the given array the maximum number from the given array correct so after the loop that particular max variable will contain a max of a given array so before the loop, what we have said, the precondition is that the initialization variables are true before the loop. So in maintenance, what we say during each iteration, my loop invariant, that is my max, is having the maximum element in that iteration. अब कोई भी इटरेशन पे आप जाओ जैसे थर्ड इटरेशन पे जाओ फोर्थ इटरेशन पे जाओ सो फोर्थ इटरेशन पे क्या होगा यू मस्ट हैव सर्व द 4 एलिमेंट्स फ्रॉम दैन एरे करेक्ट सो व्हाट आई विल से कि 4 एलिमेंट्स में से जो मैक्स एलिमेंट रहेगा वही मैक्स वेरिएबल रहेगा फोर्थ इटरेशन पे सो फॉर एवरी इटरेशन माय लूप invariant is true, my max variable is going to have the maximum of the given array. Right? So that is my maintenance phase. And what is my termination phase? So the loop terminates. When my loop is going to terminate, you all tell me when my loop will be terminating. My loop will be terminating, right? When I will be, I is equal to n. Correct? Because my loop is going to get iterated when I is less than n. So at the moment my I becomes n, my loop will be terminated. Okay, so for each iteration, अभी each iteration में क्या होने वाला है? For every iteration, the max is going to hold a maximum element of that particular iteration or of that particular array size. So after the nth iteration, after the all iteration or nth iteration, my all elements will be scanned and my max variable is going to have the maximum variable from an array. Correct? So after the loop, my max will be having the maximum element from a of I, right? And my I will reach to n. So this is how I will be getting the maximum from an array. So my termination case will be, what I will say in my termination case? In my termination phase, I say that the loop terminates when I is equal to n. So each iteration is going to have the max element, a maximum element from an array in a variable max. And once my loop terminates, once I is equal to n, this max is going to have the maximum element from an array. This is going to be my termination case. So after the loop, my a of 1 up to n contain a of I will be having my all elements, and max variable is going to have the maximum element, and I will be n. So this is my termination condition. So my loop invariant, which are my loop invariants? This max variable, which is equal to a of 0 initially and I is equal to 0. These loop invariants satisfies the condition of initialization, maintenance, and termination. Initially, they are a of 0 and I is equal to 0. Correct? During the maintenance phase, what does it happen? During the maintenance phase, for each iteration, I say that max is going to contain the maximum element from that size of an array. And at the termination condition, my max is going to contain the maximum element of an array and my I will reach to n. So this is how my correctness of algorithm is proved via loop invariant property. Am I right? I hope this is clear with all the students how to prove. See, what we are taking here, we are proving the correctness of an algorithm, right? So this correctness of algorithm is proved using loop invariant property. Now, which algorithms can be proved? Which algorithms correctness can be proved using loop invariant parent property? The algorithm which are having loops. So there are three steps in this loop invariant property. These three steps are initialization, maintenance, and termination. So now we have seen one
Good morning,
example.
ma'am. Ma'am, this is Aman. I have a doubt.
Yes, bolo.
Ma'am,